Okay, let me know when should I begin.
Yeah, go ahead.
Okay, thank you everyone so much, and sorry that I cannot be there. And my Japanese, I'm getting better right now, but still, I will present this, in English, and hope everyone can understand. And please ask any questions you have, during the presentation. So today I'm going to talk about, the lab, the directions, and also, the introduction of what we have done in here. So the lab is a taxi for future semiconductor labs. And for here, we are working on from atomic engineering and toward industrial scale manufacturing on the next generation artificial intelligence hardware. So here I'm Vincent Tang. I'm still not on campus, but I will visit Tokyo on April 5th. Yeah, so hopefully I can meet all my colleagues and also students over there. Yeah, I'm very looking forward to visiting Tokyo after 2 years. And so I will be starting my presentation right now. And first, I would like to give you a very broad introduction about what is two-dimensional atomically thin films. So you can imagine that you have heard a lot of stories about these atomically thin material. And the most representative one is graphene. But we know that since 2004, researchers at University of Manchester first successfully exfoliated monolayer graphene from graphite. And we came to know that it is 1 to few atom thick, okay, and possibly down to 1 atom thick. They are mechanically strong, yet they are very, very soft. Okay, imagine you have a material as strong as stainless steel, but it's still as soft as your clothes, right? And they have ultra high mobility. And recently they have been found that have a very strong light matter interactions. And luckily, throughout the years, we found that graphene is not the only material in this family. There are actually a lot of them. For example, so graphene is a semi-metal, depends on the layer and the number of layers. And here you have hexagonal boron nitride. It is a monolayer material, but it is an insulator and can be utilized as a dielectric layer in the transistor application. And also, you have a semiconducting material, transition metal dicalcogenides. For example, here you have molybdenum disulfide, MOS2. And also, some of my colleagues, they are very interested in, monolayer glass, the silicon oxide, and also this very specific type of material, silicon carbide. So you can see that you have a wide variety of material in this two-dimensional atomically thin films. And you have seen a lot of focus. Of course, this is a very hot field, a very crowded field. So in here, we stand out by exploring, controlling, and exploiting these novel 2D atomically thin films. Especially, we are looking into a very fundamental questions, especially from a chemical engineering system point of view. That is, how are we going to grow, process, culturize, and utilize these atomically thin materials? And I tend to utilize a very interesting example to illustrate our approaches. And I like to use color paper, right? So we learn a lot of knowledge from the color paper. So you can see that this is a stack of color papers. They have different colors. And you can imagine each color represent a specific type of the material, right? Different color, different materials. But the most important thing is that first, you need to have the synthetic capability to synthesize very uniform and high quality papers. So this is our first research direction. And after that, after you're getting these high quality materials, then you're able to stack them together, from 2-dimensional to 3D structures. Or you can form a pattern, a color pattern, and each color has different distinct functions. So for example, you can have N-type material on the left, P-type material on the right, and in the center, you will have a p-n junction that can be utilized as photovoltaics or even transistors or optical detectors. Further, you can also twist them together. You can also twist them. And this actually gives rise to one of the breakthrough, discoveries in 2020. That is the Mori patterns that holds the tantalizing, potentials to revolutionizing the memory devices. Yeah, so next I'm going to talk about the first direction in the lab, future lab right now. So we are working on the first direction is the epitaxy growth. So we are specialized at the leading edge epitaxy, especially creating a universal platforms. So meaning that utilizing one platforms, we are able to synthesize all types of the materials. Okay, and these materials will be high mobility, probably 1 to 3 atom thick, and with wafer scale homogeneity. So our approach is that we take an oxide substrate, normal oxide substrate, and we structure the surface. And we found that by structure the surface into only half unit cell thick, we are able to utilize these steps to direct the growth of the materials. So ultimately, they will form single crystal and dense align of the materials. So this gives us a capability to synthesize these high materials. And thus far, we found that this structured platform, that we are able to create a wide variety of single crystal 2D materials, ranging from N-type, molybdenum disulfide, P-type, tungsten diselenite, or semi-metal graphene. Or, most recently, we found that we are able to create these materials in stacks. For example, first putting graphene, and we can directly grow tungsten selenite, molybdenum disulfide on top of these graphene layers. So immediately you have an atomic stackings of the functional devices. So this is a vertical p-n junction devices being built over here. And this, this breakthrough leads to, the what we so-called the monolayer electronics. So everything you can ever imagine utilize silicon can be replaced by this monolayer material. So this not only leads to the extension of the Moore's law, because we know that silicon-based electronics are now facing a very pressing situation because we cannot downscale the silicon anymore. So by utilizing the 2D materials, we are able to further downscaling the devices onto molecular scale. So imagine that in the future, your iPhone will be as thin as a paper, okay, by utilizing this type of material. And furthermore, you will have the computing power that drive the hardware for artificial intelligence software. So this is actually one of our new directions. And next, since we have the capability to synthesize these high quality films, so we are able to stack them, okay, from 2D material into 3D integrated heterostructures. So you can imagine that you utilize the wafer or the structured wafer, we are able to create these materials and we stack them on top of each other, right? So any electronic function, any shape, any places, you can simply just by stacking. So this provides the flexibility in integration. So you no longer need rigid wafers. And let's go further. We could even build up any types of the functions simply by stacking these films together. So right now you can see that solar cell by stacking films, battery by stacking all these films together, even sensors. And on top of that, you can even build a with catalysis functions. So you can imagine a ubiquitous applications simply by stacking. And most immediate application that you can find, you can see that this can be utilized to drive the software to drive the smart vehicles. Or we can utilize these sensors for buildings or for smart cities, or even the skin for the human health. And this actually leads to one of very interesting and very recent directions of the lab right now. So we are working on is that how can we utilize these new materials, these new 2D materials, and to merge the human and machine interfaces, through these atomically thin films. Because let's take a look. This is a human body, right? So human body, we are soft and this are wet and they are living. But machines, they are hard, they are dry, and they are non-living. So our goal is that by utilizing these atomically thin material as the active interfaces. Okay, so our goal is that to take these materials by stacking them together, but still, because even though you stack in 10 layers, they're probably only less than 20 nanometer thick. So you have the functionality while keeping the flexibility for integration. Okay, so this is the recent direction that we are aiming for. So hopefully we could explore with you as a new student here, at the University of Tokyo after the lab is open. And this actually leads to the conclusion, of the lab is that, so hopefully we are able to utilize, these technologies for future semiconductors, especially in the materials and for industry. So our ultimate goal is that creating all these materials for artificial intelligence hardware. So this helps us to power a variety of the functions. And also we hope, to work with machine learning algorithms to further propel the function of these materials. So in the end, you can see that this is the conclusion that we have. So we try to put three things: push beyond the fundamental understandings of these advanced manufacturing for next generation materials for electronics beyond silicon. And we want to develop a very novel chemical engineering reactors for the epitaxial growth and at scale. And also, most importantly, forge links between the cutting edge research and the commercial success to drive innovation for commercializations. So you can see that there are a lot of materials, semiconducting materials, artificial intelligence units, new type of catalysis, material for catalysis, or material for electrodes for novel energy storage, memory materials, design, and even theoretical chemistry. So you can see that this type of new material will open up these new functionalities and new fields over here. So we are aiming for all the way, from meter scale all the way down to nanoscale. So everything, directly produced from these atomically thin films. So here is, what we have published from, 2020 and still growing. So if you are interested in knowing more about these two-dimensional atomically thin films, please, email me or ask me questions. I'm more than happy to answer any questions you have. So thank you so much. And again, I apologize, for my less than proficient Japanese. So hopefully, in the future, I will explain to you all these things, exciting discoveries in person. So thank you so much for your patience, and I'm looking forward to meeting you all at the University of Tokyo. Thank you so much. And thank you, Saori. Thank you.